Alright, as usual, let's start off this video with a challenge problem from the last video. So we have two objects, one is on the moon, one is on the earth, and they both experience the same gravitational force, or you could say about the same weight. So which of the following would be a reasonable conclusion? Well, we could say weight or force due to gravity equals mass of the object times the gravitational acceleration at the given location, and the moon has a much smaller mass, therefore it has a much smaller gravitational acceleration compared to Earth. So in order for the objects to have the same weight, the object on the moon has to have a greater mass than the object on the Earth. Problem: we have two satellites with orbits of r and 2r about the same planet. If the orbital velocity of one satellite is v, then what would be the orbital velocity of the other satellite? And as you can see, we are solving for it in terms of that v. Alright, well, we know our equation for centripetal force is mv squared over r. And of course, I strongly encourage you to try and figure out the answer to this problem on your own and then come back to the video to see if you were right. And in this case, the centripetal force would be the force of gravity that is keeping these satellites in orbit. And we know that is g times the mass of the planet times the lowercase m for the mass of the satellite divided by the radius of orbit squared. Well, we can cancel out the mass of the satellite and one part of the radius of orbit, and then we can see that our velocity is equal to g times the mass of the planet divided by the radius of the orbit, and take the square root of that. For this problem, we have four satellites orbiting a large planet, and their masses and radius of orbit are given below. We want to know which one has the greatest speed. Alright, well, we know speed, orbital speed, is in our equation for centripetal acceleration, and it's also in the equation for centripetal force. Alright, so because centripetal acceleration is part of the equation for centripetal force by Newton's second law, let's use that equation. Alright, so we know the centripetal force on each planet is due to the force of gravity, which we know is g times the mass of the planet, which is the same for each of the satellites, times the mass of the satellite divided by its radius of orbit squared. And we know by Newton's second law it's equal to m times centripetal acceleration, and m is the mass of the object that is making the orbits, so the mass of the satellite times its velocity squared, which is essentially its speed, again divided by r. So we can cancel out the mass of the satellite, which means that this entire row here is insignificant, and one of the r's. And that gives us that our speed is, so we've got speed equal to the square root of our gravitational constant times the mass of the planet divided by the radius. And that means that the speed of the satellite is inversely proportional to its radius of orbit. Therefore, the smaller the radius, the larger its orbital speed is going to be. And you can think about that if you're like have an object on the end of a string, you're spinning it in a horizontal circle. The smaller you make that radius, the faster that object is going to spin. So of our options, the satellite with the smallest radius is B. That satellite will be orbiting the fastest, and A and C will have the same speed in orbit, and D will be the slowest if you were to rank these. Problem: we have an asteroid of mass m and speed v orbiting a planet of mass large m, and we are looking for the radius of this asteroid's orbit. So we know there's a force of gravity acting on that asteroid to keep it in that stable circular orbit. So say this is its path, there's the asteroid, and there's the force of gravity pointing towards the planet, and that would be the only force that we have to account for. I mean, there might be smaller forces of other asteroids, planets, or moons on it, but right here we're only concerned about the force of the planet. And we know that's equal to the mass of the asteroid times its centripetal acceleration. So we can set a gravitational constant, mass of the planet, mass of the asteroid, divided by its radius squared, equal to the mass of the asteroid, its velocity squared, divided by that radius. Alright, so we know that the mass of the asteroid cancels, and we can multiply both sides by r. Alright, now let's just take a look at our options and see if we can cross any out. A and C both have the mass of the asteroid in it, and we've already gotten rid of that variable, so we're left with B. Actually, D cancels out too, so it looks like B is our answer. However, we can double check by multiplying both sides by r and dividing by v squared. And that will leave us with r equals, let's see, these variables cancel, g times the mass of the planet divided by the velocity of the asteroid squared. So B is the correct answer for this problem. Alright, this will be the last practice problem for this video. So we have a satellite moving in a uniform circular orbit with a speed v0 at a distance r from the center of a planet, and we want to continue this uniform circular orbit at a distance 2r from the planet. So what must the satellite's speed be? Alright, well, we know that if this were to be our satellite, this is its orbit, has a force of gravity directed towards the center of the planet, and that is g times the mass of the planet, mass of the satellite divided by r squared. By F equals ma, we then get mass of the satellite, speed squared, divided by radius. We can divide both sides by the mass of the satellite and multiply by the radius of the orbit, and then we get that its speed equals our gravitational constant times the mass of the planet divided by the radius of orbit, and we take the square root. Alright, now we see that our radius is in the denominator of this expression, so if we were to double the radius of orbit, our velocity is going to decrease by the square root of 2. And option B is the only answer where that happens. So here's the challenge problem for this video. The solution will be on my Instagram page about 24 hours after the release of this video, or you can find it at the beginning of the next video.